Hey everybody, welcome to PC Perspective. Today we finally reveal the full process, results, and information about our new graphics testing method called frame rating. If you've watched any of the previous videos or seen any of the previous kind of preview articles that I've posted since about January of this year, you know about our new process of capturing video from a test system, analyzing that video, and measuring frame rates, frame latency, stutter, anything like that in a completely new process and method that we are calling frame rating. Well, today is finally the day where we can reveal all of the process, all of the steps, all of the software that we are using for these new kinds of benchmarks. We're going to go over that. We're going to run and show you some of the results from a couple of cards, the 7970 and GTX 680 in single and dual card configurations, and then we'll release more results as the week goes on. But for today, we wanted to focus on explaining our process, explaining the results, explaining what we think those results mean, and start a dialogue with the community, with other review sites, with other readers, and kind of get the ball rolling in terms of let's talk about what this means for PC gaming, what this means for graphics performance going forward. So the first thing we're going to do is we're going to actually walk you through the process of how we capture video, analyze it, and actually create the graphs that you see in our story today. So the first step in the frame rating process is actually on the testing PC where you have the overlay application. Now what the overlay does is it draws a single column of color on each frame as it leaves the game engine. Now it draws a single color, and we have a pattern of 12 or 16 colors that successively goes through the list. But as the frames are displayed on the monitor, you'll notice that there will be several colors on the left-hand side indicating the several frames that are shown up and actually displayed in each display refresh cycle. Now running that is actually pretty simple. It's just like maybe starting up FRAPS or anything like that, and then you start the game as you normally would. So if we go here and we enable the overlay, it's just a simple application that does some DirectX hooks and that kind of thing. And then we'll go ahead and load up Crysis 3 and show you the overlay at work. So you can start to see the colored bars show up on the left-hand side. And while we had a teal-colored bar at first, that was because there was only one frame that's being displayed. And now that we have many frames being displayed, you'll see a rainbow of colors that don't make much sense, honestly, in real time. You can't really tell much information from them. Once you get used to know what you're looking for, you can tell some specific things from the patterns. But let's go ahead and load up a mission here so you can see again the pauses here as the game is loading, and then we will actually get into some gameplay, and you'll see that same kind of rainbow pattern, the successive colors, and that is basically what the overlay does. It applies these colors so that we can record the video and then analyze that video after the fact. So let's go ahead and load up the game, and I'll run through just a little bit here so you can see what it looks like. Obviously you don't want to game in this kind of situation, right? This is basically for testing and performance evaluation only, and to really, it could give you a headache, distract you if nothing else, at the very least, with all that color going on the left-hand side of the screen. The second step in frame rating is to actually capture and record the video from the graphics card. Now it sounds really easy, but it turns out it's not. It requires a lot of very specific hardware, very specific software with very particular types of settings. So here you can see we're still running Crysis 3. Rather than taking a DVI connection straight into the monitor, what we do now is we take the connection out of the graphics card setup into a dual-link DVI splitter, which allows us to mirror the outputs essentially, but without the graphics card or AMD or NVIDIA or whatever having any knowledge that that's going on. And then we pass one of them to our monitor and one of them to a special system that we built, a completely separate system that we built for video capture. Now the most important part of that capture system is actually this. It's a dual-link DVI capture card from DataPath. It's called the Vision DVI DL. We've actually had one of these in stock at our offices here for about a year, playing with it, working with the developers, fixing driver changes, all that kind of stuff. It's a very simple looking product, but it's very specific in what it actually does. It has a single DVI, dual link DVI input on the that we capture the video from. So it's capable of, technically it's capable of resolutions 2560 by 1600 at 60 hertz. We've kind of found the limit to be 2560 by 1440 at 60 hertz, but that seems to be close enough, and it's a pretty common gaming resolution as well. Now, when we captured on this system, we're also doing, we're actually using a Thunderbolt external RAID array for our capture. It requires, when this capture card is at its peak, it's doing almost 600 megabytes per second of writes, so you need very, very fast and reliable write speeds. We're using a Pegasus R4 array Thunderbolt connected to an Asus Z77 Thunderbolt motherboard with the Thunderbolt EX card installed in that. And then we have 4 240 gig Corsair Force series SSDs in there as well. So we have almost a terabyte of SSD. It's running in a RAID 0 array for maximum performance. So we've got almost a terabyte, and we fill that up very, very quickly. A single 60-second run at 25 by 14 resolution takes up about 25 gigabytes of data at one time. So it's actually, there's a lot of data involved in this process. Now, once we are in the game, you actually have to use two systems to do this. We have our software here that we've kind of written just to kind of make the process a little easier for us. We can set a time limit to how much we want to capture. For this particular demonstration, I'm just going to show you that we hit capture or capture with analysis. I'll just capture only here so that we can show you the analysis steps separately. So if I go ahead and hit the capture button, you see a little timer comes up, and then I'll just go ahead and play the game as you normally would in order to, simulate gameplay. You're doing benchmark. This is what we do for all of our benchmarking and all of our graphics reviews now. So there's, we've captured a short video. Normally we're doing 60 seconds or more. This one we just did 15. And the result is a 3.6 gigabyte file, AVI, recorded through a piece of software that we're using called GraphEdit that uses DX filters. Some people will be using Virtual Dub for that. It's the same idea, although this is just a little bit more efficient for our use. Now, when you open up this video in Virtual Dub, and we'll shrink this down a little bit here so we can get the full frame in, what you see is we have the colored overlay on the left-hand side, and we can actually step through each individual frame. If we play it back at full speed, you get the same kind of rainbow effect. If we hold down the arrow key and go through it in slow motion, you can see the colors a little bit clearer. And then when we step through them frame by frame, forwards or backwards, you get to see the colors at work. Now, there's a very specific pattern to this. I almost have it memorized by heart now. It goes white, should be followed by a lime overlay, followed by blue, red, teal, navy, green, and so on. And so this allows us to use a separate application to measure the length of those bars, find out frame times, find out frame rates, as well as look for specific things like runts and drops, any kind of anomalies that may happen in the graphics pipeline. Now, so this all works okay. We've got the colors in the right order. And the next step we'll actually get into is analyzing this data and showing you the Extractor application and how it generates a huge amount of XLS data out of one of these videos. The Extractor is actually a program, one of those ones that NVIDIA helped write, that will take the video input, the video that we just captured, look at it frame by frame, measure the lengths of those colored columns, and then output the information that we need. So this is kind of the application as it works. We kind of built our program so that we could drag and drop some things and get some easy to see data. So you can see here's the Extractor at work. It's analyzing the frames. You can see that there are 900 frames in this 15-second capture. Pretty straightforward stuff. So if we go into this folder, we actually see what it has been generated. There's actually a whole lot of files here, but the one that the Extractor application actually creates is this rather large XLS file, which is a bunch of tab-separated data. And you can see for every frame and for every color that it sees, it's generating things like the frame number, the scan lines, number of scan lines that it counted for that color, the amount of time in milliseconds that color was on screen, what the instantaneous frame rate it creates is, frame starts, screen refreshes, the colors in hex code. All right, and that's kind of the raw data that you then analyze through a Perl script. That is the FCAT that NVIDIA has built, the FCAT collection of tools, frame capture analysis tools that they built. And it generates graphs that kind of look like this. And you can do whatever you want with this data, and actually you'll see in our review that we're using much more complex graphs. We're using other GNU plot settings and analysis to give you different statistical modeling based on this information. But really the key is getting the recording, getting the overlay, getting the recording, getting the extractor to measure those scan lines, what colors are there, what colors aren't there, and then you kind of analyze the data, create the graphs, model the information however you want. And you can see in our testing that we have many, many, many different runs with all the graphics cards from the 680s down to the 650s, from the 7970s, 7770s, and all that kind of stuff down through this list. Now in a best case scenario, you get what we had there, you get all the colors in the right order, things are very consistent. When things aren't working out perfectly correct, this is the kind of stuff that you'll actually see. If we open up this 7970 Crossfire video recording and we shrink the size down, this is actually done at 2560 by 1440, you start to see some interesting patterns. And this is something we've talked about already in some of our frame rating videos, I think the second and third one, where we talked about the idea of what a runt is. And actually I'll zoom in here a little bit more. And what you'll see here is we've got this navy color, and then you've got green, and then you've got aqua. And that is actually the correct order that these colors should be in. Nothing's getting dropped or anything like that. But because this frame is actually being shown for such a little amount of time on the screen, it's not really helping the animation that you're seeing. It's not making anything smoother. And if anything, it may be actually making things quite a bit worse because you get these interesting tears in the video, in the gaming frames. So if you cycle through here, you'll actually see that it's pretty consistent with a lot of our Crossfire results that every other frame, as you'll see here, is a runt, right? So we kind of cycle through those here, and you'll see a bunch of that kind of stuff. And that is part of the analysis part is figuring out what that means, figuring out how that affects gameplay, how it affects the animation smoothness that you see. And it actually kind of rolls into our collection of graphs that we are presenting. This is something that's fluid, it's something that's changing, and we're definitely looking for feedback from readers and viewers to tell us what they like about certain things and what they don't like about certain things. So in this particular article, what we're going to show you are 5 different types of graphs. All right, and this first one right here is simply what the frame rate would be, average frame rate per second that FRAPS would normally report. This counts runts and any drop frames in the same manner that FRAPS would. It sees them, it measures them, but it averages out over the second. So you can see here that the 7970 Crossfire is well ahead of the 680 SLI in blue, and then the single cards are actually relatively close with the 7970 being ahead. The next graph that we are building is something that I'm calling the observed frame rate. And this is taking away any runts, taking away any drop frames. If we literally take those frames out of the picture, because I decided that they adversely affect performance or are not affecting performance at all in real world experiences, this is the frame rates that you get. You'll see that the frame rates tend to be much lower. They tend to be a lot of spikes, a lot of highs and lows. And performance in many cases is very similar, sometimes even worse than a single card when we compare 7970 to 7970 Crossfire. What you'll notice though is the 680 SLI is still much higher than the 680. It's still kind of scaling as you would normally expect. Now if we look at the percentile graph, this is interesting because we are taking every frame time that is generated by the FCAT tools and by our capture method, and ordering them and creating a percentile graph. And we're showing you 50 to 99. And what you want to see here is you'll find that this 50th percentile, this first kind of measure right here, is going to be very, very close to your average frame rate over the entire length of the run. So you could say that the 680 SLI is going to average about 141, 142 frames per second at 1080p, whereas the 7970 Crossfire is closer to 102, 103 frames per second on average for over the entire 60-second run, and that is because of the observed frame rate, right? So this takes into account, this takes out all the runs, it takes out any dropped frames. And then you can see below that you've got the single cards. Now what you would want to see here is as close to a level line as possible. You want to see as little drop off as possible, kind of down here. You want it to be as even as you can. That means that there are a lot of consistent frame times. Now when we look at this plot, this is maybe what you maybe are used to seeing now with frame time graphs, and this is you know, actual frame times in a plot, and in this you see the thinner the band of color, the better. That means the tighter the frame times. Green and black here represent the single cards, 7970 and 680, and they're pretty good. The blue here represents the 680 SLI, and it's definitely more frame time variance than the single cards, but it's pretty good. And then the orange is the 7970 Crossfire, and that is what you're seeing is alternating back and forth between one long frame, one short frame, one long frame, one short frame. And again, kind of results back to our observed frames per second. And finally, this is one that we are trying out a new algorithm with. This is frame variance. And so basically what this does is we take each frame time and compare it to the running average of the last 20 frames. And we see what the difference between the current frame is and the running average of the last 20. And ideally what you want is that to be as low as possible. You want the frame variance to be as low as possible. And so we, again, arrange this in a percentile format. And the steeper the grade, the earlier that the line goes up, the worse your frame time variance is, and the more likelihood you will find image stuttering, animation stuttering, and inconsistent animation rates, I guess. So you can see here, 7970 Crossfire, it definitely goes up quite a bit quicker than anything else, while the 680 SLI stays pretty good up through the 80s and the 90 percentile range and does kind of creep up a little bit. And then the single cards do pretty well all the way through the end. And I'll just run through the 2560 result. Here's our FRAPS reported frame rate. Here's our observed frame rate. Again, you see Crossfire is basically down to almost the same performance levels as a single card. Here we look at the percentiles of minimum frame rates, and you can see how the average here at the 50 percentile mark is affected by the runts in Battlefield 3. And then here's our plot, and you can see again the huge mass of color that you get with the orange that represents the small frame, large frame, small frame, large frame oscillation. And then here is our frame variance stutter detection type tool, where you see that it definitely, the 7970 Crossfire peaks up way, way, way ahead of anything else very, very early in the 70 and 80 percentile range. Now that you have a better idea of what all of the graphs we're presenting mean and what the data is, you definitely need to go to PCPer.com and look at the entire story that we published today. It's a really long story, and so long in fact that I decided to break it up into multiple pieces. Today's release focuses on just the Radeon HD 7978 GHz edition and the GeForce GTX 680 results, both single and dual GPU. And throughout the week, we'll release 7950, 7870, 7850, and then obviously the NVIDIA side as well, 660 Ti, 660, 650 Ti, those types of things. So we're going to break that up and kind of segment them as the market has segmented them as well, just to prevent data overload on the outset. It's important to note, though, that the runting issue, the runt issue that we saw with the Crossfire results early on in this video, are repeatable, and it happens not just on 7970s, it happens on 7950s and the 7870 and 7850 and on down the line. And it happens with about 50% of the tested games that we've looked at so far. We're actually starting out with just 6 games, but we plan on expanding that to look at all of the new games as they're released to see how SLI and Crossfire compare in that way. So, you know, we have a whole lot more to do, but I feel like the results that we have are very compelling. They paint a very unique story of graphics performance. That Crossfire definitely has some issues. SLI, with its hardware frame metering, has solved a lot of those issues, but both vendors look fine on single GPU performance. And in fact, if you're only going to buy a single card, our results, the frame rating results, show you that the 7970 is still probably a better option than the GTX 680. But if you are going with dual GPUs, or you think you may go with dual GPUs or 3 GPUs and beyond, that you definitely need to think hard about what you want to do. Crossfire has issues. AMD is aware of these problems. We've talked with them several times about it, and they promise us that a solution is coming, although probably not for 60, 90 to 120 days to actually get a global kind of fix for this type of thing. As I mentioned, the article will have a lot more detail on this. You guys really need to go read that. And I want a whole lot of feedback from anybody in the community and forums, comments, this YouTube video post, anything that you want to do. We want to get feedback from that. We have things like, we have our VSync testing in there as well. After our third preview story on it, a lot of people said, why not just enable VSync? What does that fix? How does it change things? And we have the answers to that in our story as well. So please encourage you guys to go read the whole article, leave us feedback. This is a dramatic change and a dramatic shift for not just our website, but I think the entire hardware testing industry as it goes forward. So it will be an interesting ride from here on out. I'm Ryan Shrout for PC Perspective. Thanks for watching.